So we got to example letter C. So let's go ahead and look at letter D. So number one, let's determine the type of indeterminate form for this limit. And again, the substitution rule is what we're going to do in this case. So we have here we have the limit of sine up to x over 5x as x approaches 0. So let's plug in sine. Oh, okay, so that's sine of 2 times 0. Well, that's sine 0, but sine 0 is 0. And 5 times 0, which is also 0, which is good. That means L'Hopital, the L'Hopital's rule apply. So let's write down LH to denote that we are using the L'Hopital's rule. And so to do the L'Hopital's rule, remember that we do the derivative of the numerator and the derivative of the denominator. Recall it's not the quotient rule. Okay. Limit x approaches 0, the derivative of sine, which is cosine to x, but in this case it involves a mini chain rule because this is a composite function. We need to multiply by the derivative of the quantity inside a parenthesis. In this case, the derivative of 2x is 2. And finally, the derivative of 5x is 5. So we can, okay, let me rewrite this. And in this case, I guess we can plug in the value because in this case, cosine of 0 over 5, cosine of 0 is equals to 1. And 2 times 1 over 5, so 2/5 is the answer. Right? So just a little comment on the notation that we use. So recall from Calc 1 as well that every time we're working on a limit problem, we need to keep the limit notation all the way. So until we plug in the value, until we use the substitution rule, that's where we no longer write the limit symbol. Okay. So let's see, let's have a look at letter E. So how about you guys look at letter E? How about you try on your own, take a couple minutes, see what you get, check what the indeterminate form possibly is, and then from there, just apply the L'Hopital's rule. All right, do we agree with the indeterminate form in the first place? Yes. Is that an infinity over infinity? Okay, so that means L'Hopital's apply. So let's see what happens. So limit x approaches infinity, the derivative of x squared equals to 2x, and the derivative of e to the 2x is itself the exponential times the derivative of the exponent, which is 2. Okay? So in this case, well, we need to check whether we still have an indeterminate form by substitution. And again, it seems like infinity over infinity is the case in this case. So let's do the L'Hopital's rule again. So that derivative of 2x is 2, and that's going to become 4e to the 2x. And 2 reduces with 4 to 1/2. And in this case, well, where is this limit going to go as x approaches infinity? 0. All right. Questions about it? All right. Let's see what's on the next page. All right, so for the next page, this is where some of the indeterminate forms start getting a little bit weird. So we will no longer get the infinity over infinity or the 0 over 0 in the first instance. So let's see. What are we going to do about this one? So let's plug this in at infinity. So on the one hand, okay, let me do the scratch word below. So that's going to be infinity times sine of 1 over infinity. But what's 1 over infinity? 0. So what do we have? Infinity times sine of 0, which is 0 times infinity. And well, that's one of the indeterminate forms. All right. However, that one doesn't really look like a quotient, you know, like a 0 over 0 or an infinity over infinity. So whenever we have one of these new crazy looking indeterminate forms, we need to find ways to turn them into indeterminate forms that we know from the other forms. So this is what we're going to do. So we need to make sure this looks like a quotient. So let me do some algebraic manipulations here. So limit x approaches infinity. In order to make this look like a quotient, well, think of the following. If you agree that, for example, this value of x, or this expression x, is the same as 1 over x to the negative 1 in the denominator. So that's the trick we're going to do here. And at the same time, we're going to move this x in the denominator of the sine function with negative exponent. So now it looks like a quotient to me. And well, so what is this going to be? Well, so we're clear to do the L'Hopital's rule. All right. And well, what's the derivative of sine in this case again? Isn't that a cosine, I believe? Cosine x to the negative 1, but in this case we need a mini chain rule. We need to differentiate that x to the negative 1. We need that general power rule, and be careful with the negative sign. So that's going to be negative x to the negative 2. And in the denominator, the derivative of x to the negative 1 is also negative x to the negative 2. So in this case, well, even though it looked a little bit crazy expression, this one is going to simplify really, really nicely. So what we got? So limit x approaches infinity of cosine of 1 over x, that's fine. And well, we already saw that this goes to 0. This is cosine of 0. And cosine of 0 equals to 1. Questions about this one? All right, have a look at letter G. take a couple of minutes and have a look at letter G, and notice how this limit has a different notation than other ones that we have done before. Notice there's an integral in there. And notice how this integral has more than one variable. Sure, that might bring some memories from Calc 1. See if you can see what it is. Of course, talk to the person next to you and compare results, share ideas.
I just wrote it because I was just kind of bugging me on the side. I was like, I don't understand what it is.
Yeah, I was trying to solve this first, but I was telling May that if you make this 10 minus t squared and u, then your d, you still have a t. So
Yeah, and so I was like, at first I just was like, did he put something wrong?
and then I thought we could factor it like if it's just squares, but
Yeah, I've never seen anything like that, so I was like, I have no idea what you're talking about. Yeah, I was like, it was like nature wise, I almost
I was just rewriting it.
yeah, I see what I was like,
well, if you think about it, you're plugging in 3, right? So from 3 to 3, when you're doing a limit from the same one to the same one, isn't it just 0? So you have 0 over 0. So if you do the derivative of an integral, then it cancels out, and then you can move on. Okay, okay.
yeah, I said like almost like they weren't matching like yeah the D of G or something like that every kind of was like what?
So, and here's equation 3, and then you can do the derivative of this.
All right, let's have a look at this one. Again, regardless of how a limit expression looks like, what is the first thing we always try? Plug it. What do we plug in? Let's be more specific. The value that x is approaching to, right? So, and check this out. So in this case, notice the x is here and here. So let's see. So no more limit symbol. That means the integral from 3 to 3 of the square root of 10 minus t squared with respect to t, and then that's a 3 squared minus 9. Okay, 3 squared minus 9, that's 9 minus 9. That means 0 in the denominator. And the numerator, what do we get when we have the same limits of integration for an integral? 0. I mean, recall that the integral represents the area under the curve on a function from point A to point B. But I mean, if you remain in the same point, I mean, you're going from 3 to 3, you're standing at the same point. You're not spanning any area, so 0. All right? Which is good, because this is an indeterminate form. Let's do the L'Hopital's rule and simplify this one. So limit, let's denote the derivative. I didn't do this in the other exercises, but just to be more explicit with the notation for this particular case. That's the square root of 10 minus t squared dt, and the derivative with respect x of x squared minus 9 as x approaches 3. All right, the denominator is the derivative of the denominator. It's just 2x. But the numerator, the derivative of the numerator, well, what happens when you integrate regardless of the limits, regardless of the function, but then you apply the derivative operator again?
Isn't it the original?
Isn't it the original? But in this case, one of the limits is x in here, you know? So all we get right here is just the square root of 10 minus x squared. All right? And yes, I know you might be thinking, I'm missing the term for the evaluation of the lower limit, but that lower limit is a constant. And when we plug it into that radical, we're going to get a constant. But because we're differentiating it, what's the derivative of a constant? Do we really need to write it down? Not really, right? So I think we're in good place to compute this limit. Let's plug in 3. Yes, that's not going to give us a 0 in the denominator. That's a 10 minus 3 squared over 2 times 3. So what do we got? What do we get here? So that's going to be 10 minus 9. That's 1. The square root of 1 is 1 over 6, which is 1/6. All right. Questions about this one? Yes.
Let's say you had the same integral, but instead of an x at the top, there was like a 5 or something. Doing the derivative of that, would it still give 0?
0. Mm-hmm.
Oh,
So
0?
because it's a constant, so in this case you will be integrating from a number to another number. You will be getting a constant value for some area, and take the derivative of that number. That's going to 0 out.
Okay.
Mm-hmm. Yes.
How do you get the, wait, how can you replace the t with the x?
Okay, that's a good question. Let me do that in a slower motion here. So I think it's great to go over those details. So the derivative with respect x of the integral from 3 to x, 10 minus, what is it, t squared, right?
Yes.
With respect to t. Well, in this case, if we wanted to evaluate this integral, we don't have tools yet. Unless you have seen integration by trigonometric substitution before, but in this case, we are assuming that you haven't done this before. So, well, in this case, think of this as an f of t. All right, f of t. Okay. So I'm going to take the derivative with respect x from 3 to x of f of t, all right, with respect t. Well, in general, when we compute the integral of some little f, we're finding its primitive or its antiderivative. Well, different vocabulary depending where you read all this vocabulary. So that's the derivative with respect x. Well, no longer integral. We already integrated some f of t rather, whatever that is. We don't care, because we will differentiate it anyway and get back to the original function. However, this function gets evaluated from 3 to x. All right? Using the fundamental theorem of calculus, we get, well, let's keep writing the derivative with respect x of big F of x minus big F of 3. All right? So in this case, okay, let's distribute the operator d dx of f of x minus d dx of 3. Okay, f of 3 rather. So this is a constant. Do we agree when you plug in just a single number? What's the derivative of a constant? 0. Okay, what's the derivative of big F? Small x, right? But what's f of x? So just replace the original function, just change the letter. All right? That's 10 minus t squared minus 0, x squared. I didn't replace it. All right. Well, things get a little tricky when one of those limits, it's no more just x. What if we have the same integral? And I think it's worth looking at these ones. Let's say I have an x cubed. All right, same integrand, 10 minus t squared dt. All right. So again, we will integrate from 3 to x cubed some little f of t with respect to t. And then from here, so that's big F of t, but now this is evaluated from 3 to x cubed. And again, upper limit minus lower limit, f of x cubed minus f of 3. All right? Basically the same for now as before, but now when we distribute the operator here, so that's the derivative with respect x of f of x cubed minus the derivative with respect x of f of 3, which is just a number. That's going to be a 0. But in this case, be careful, because what's the derivative of big F again? Little f of x cubed. But notice the composition. So we need to do a mini chain rule by multiplying by 3x squared, which is the derivative of the function. See the difference when we have just plain vanilla x versus something more, more elaborate? So we need to take all those things into consideration and be careful. So this t squared x cubed, and that's going to be the square root of 10 minus x to the 6th power times 3x squared. So it's a whole different result, but essentially the same process with a little twist in here that we need that mini chain rule part. All right?
Can you just pull it up a little bit?
Oh, of course. Yep.
Thank you.
You're welcome. Any other questions about it? Okay, let me know when we're all ready for the next example. Right? We're all good? Okay, so limit 1 over x raised to the x power. Again, this is going to be one of the weird ones. That's a typical exam question, one of those problems that, as opposed to the ones that we have done before, you just follow the line, applying L'Hopital's rule whenever appropriate, So, but in this case, we need to rewrite the problem in a different way. So, number one, let's see which indeterminate form is. So, what do we have? So, that's a 1 plus 1 over infinity raised to the infinity power. So, that's 1 plus 1 over infinity, which is 0, raised to the infinity, which is 1 to the infinity, which is good. All right? Because that's one of the indeterminate forms. But the thing is, how do we make this look like a quotient? This one is not like letter F, actually, where we were able to just bring down the x with negative exponent, derivative of the numerator, derivative of the denominator. No, unfortunately, it's not the case. It's a little bit more elaborate than that. We have that x in the exponent. So in this case, we're going to take a different approach. What we're going to do, well, this limit, whatever that is, will be some number y. All right? So set this limit equal to y. Okay? Well, we have We have a lot of tools, of algebraic tools to do some arrangements here. In particular, we have some of the properties of logarithms. Recall that those logarithms, those powers can become coefficients. So in the first place, let's take ln to both sides. All right. Now, there's a very important property of the logarithms, the one that says when we have a to the ln of x equals ln of x to the a. That's I don't know if you have heard of this name before. That's the smackdown basketball rule. So if we do it this way, that's the basketball. But otherwise, when we do it this way, that's a smackdown rule. All right, and we're going to use this rule a lot in this section. And of course, later when we go over infinite sequences and series, so let's apply this over here. Let's have this x to jump in the front of the ln x. All right, ln of y equals to the limit x approaches infinity of x ln of 1 plus 1 over x. Well, that doesn't look like a quotient yet, but from here, we can write that x in front of the ln x in the same way that we did it for the trigonometric form in letter F. So we're good to go and do that one. So this is what we're going to do. Ln of y equals the limit of as x approaches infinity. Let's write down this x as x to the -1 in the denominator. And at the same time, I'm going to write this 1 plus 1 over x, which is the argument of this logarithmic function, 1 plus x to the -1. This way will be a lot easier to differentiate. All right? Questions up to this point? Yes?
Why when you do the ln, it goes inside of the limit and not outside of it?
It's fine. It's either way. It's by the properties of limits. That's a good question. So whenever we have a limit, so that's okay, limit of, or rather ln of limit of f of x, x approaches some value a, that equals to the limit of ln of f of x. You know, these are just interchangeable. In just the same way, for example, when we have the limit of the square root of some f of x, this is the square root of the limit of the function. These are just some properties of the limits, all right? And I mean, technically, I should have written the ln in front of the ln, but just to well, it's a step that it's fine to skip, if you will. So from here, we can take the derivative of the numerator and the denominator. So let's see, ln of y equals the limit. Okay, the derivative of ln is 1 over the quantity inside of parentheses, which is 1 plus x to the -1, times the derivative of that quantity inside of the parentheses. And well, the derivative of that is going to be, well, the derivative of 1, which is 0, and the derivative of x to the -1, which is going to be -x to the -2, which is the same in the denominator, -x to the -2. All right? And yes, this one looks a little crazy, but notice how this reduces really, really nicely. Let me keep going here. So we will be left with the following. We will be left with ln of y equals to limit 1 over 1 plus 1 over x. And well, in this case, we have a complex fraction. Do we really need to simplify this complex fraction? Not really, because see what's happening here. Where is this quantity going to go for x towards infinity? 0, right? So we're going to have ln of y equals to limit, or not, no more limit, 1 over 1 plus 0, which is 1 over 1, which equals to 1. All right? Are we done here? What else do we need to do here? We need to undo the ln. So we took the ln to, so to do some algebraic manipulation. So now we undo the trick, right? So exponentiate both sides on the same base as the logarithm. In this case, it's the logarithm of a base e, also known as the ln. And cancel, cancel. That's y equals to e. All right? Questions about this one? I know this one is one of the longer problems. Yeah, this one involves a little bit of knowing these logarithmic properties, and same for letter I. All right, let's have a look at letter I and see what's the indeterminate form in the first place. So let's see. On the one hand, okay, let's substitute 0 to the 2 times 0, and that's a 0 to the 0 power, which is a good indeterminate form. That means we can use a few algebraic techniques, make this look like a quotient in a very similar way that we did for letter H. All right, so let's see, let's set it up. This is going to be a y equals something, limit x approaches 0 from the right, x to the 2x. All right? Okay. How about you take it from here, take a few minutes and see what you get? Of course, talk to the person next to you, share ideas, share your work. Are you getting stuck? Raise your hand. I will be more than glad to help you. All right?
So it's ln of y.
Yeah, the whole thing goes on the 2x.
Bringing to the front of 2x, right?
Yeah.
Okay, just confirming for me. I just do my stupid stuff. I don't want to write and be like, oh. The other teacher was funny. He was like, you have to go to the front. I was like, okay. In my mind, I said a stupid sound.
Can you still, I got to this point and I noticed that the ln of 0 is, when I tried plugging in, it was enchanted over 0.
Oh, yes, that's why we have this plus, right? Because when you look at for the graph of ln of x,
I guess that makes more sense.
right? So the limit, the sine limit is only defined from the right, so that's why I needed to be very specific. If I said only x approaching 0, that's where we need to check both sides on the behavior, and well, over here the function is undefined, there's no function, so that's why we put that little plus in there.
So, wait, so you can't do a hospitals because it's not 0 over 0 or infinity over infinity? This one's infinity over 0 or negative infinity over
Ah,
infinity.
interesting, right? So, well, this one right here is the same as saying 1 over x. So it would be worth to look at the graph of 1 over x.
Oh.
Where is it going from the right?
From as it approaches, okay.
All right.
Oh. Okay, so on the top, this is the 2 ln of x. So as you push 0 to the right, I didn't do any hospitals because, yeah, this is, well, I thought it was this, but I was just looking at it as a single
let's have a look at this one. Okay, so we got to the point here where we were setting up the problem. Let's take a length of both sides and use the smackdown rule. Looks like most of you were comfortable with this as I was walking through the room. All right, and then from here, this is what I noticed. Some of you were rewriting this 2x, both factors in the denominator, but in this case, it's only the x, the one that goes down to the denominator. So that is limit up to, well, actually ln of y equals limit to ln x over x to the negative 1, all right, as x approaches 0 from the right. That little plus on the top of the 0 means we are looking at the limit from the right. And this is very important. We will discuss why in a couple of minutes. Well, so what happens if we try L'Hopital? Well, if we see if we can apply the L'Hopital's rule again. Well, let's plug in. What's ln of 0 from the right? And what's x to the negative 1 from the right? Well, some of you put a 0 for the denominator. Let's have a look at this one separately. Actually, it would be great if we rewrite in this case to ln x over 1 over x. And there's a really, really big purpose of having that plus on the top of the 0. You will see why. So in this case, well, let's have a look at the graphs of these two functions individually. Well, on the one hand, the graph of ln x looks like, forget about the 2, don't worry about it. Ultimately, we just want to look at the end behavior. So in this case, we are approaching from the right. Where is this limit going to? Negative infinity? Negative infinity. All right, that means negative infinity over, let's look at the graph of 1 over x. Which looks like this. All right, now from the right, where is this going to? Positive infinity in this case, right? And well, again, there is a big purpose of having that side limit coming from the right, because if you analyze the ln function, what if in this case I said instead x approaches just plain vanilla 0, not 0 from the left or from the right? Well, when we have limits at approaching a value, exactly the value, not from either side, well, we need to look at what's happening on either side, from the left and from the right. From the left of ln x, no problem, negative infinity. But what about from the right? From the right, there's not even a graph. The function is undefined. So in that case, simply the limit d and e, and well, all this work would be worthless. But the fact that we are specifying from one side, it's meaningful in this case. So, all right, we're ready to do the L'Hopital's rule. So I'm going to take it from here. Ln of y equals the limit x approaches 0 from the right, 2 over x, that's the derivative of ln x, of 2 ln x, and negative x to the negative 2. All right. So in this case, let's clean this up. So let's have this, well, let's have this negative. So that's negative 2 over x. And this x to the negative 2, let me write it in the numerator as x squared, which actually reduces with the x. So that's a negative 2x. And well, this limit will be a 0, because 0 times -2, that's a 0. And again, don't forget to undo the trick by exponentiating both sides. And y equals to 1. Sounds good?